He's a Thomas Dudley Cabot Professor of the Natural Sciences at Harvard University. Professor Narayan is a world authority on a very simply asked question. If black holes are black, how do we know they're out there? He's done enormous amount of work on this issue because it's, well, we still have to see them, observe them, and he's done enormous amount of work on gravitational lensing and, of course, the physics of accretion disks, which is the main way of seeing black holes.
You're okay? Good. Thanks, Partho. So it's a pleasure to be here at this conference to celebrate a great Indian astrophysicist. And for me, it's an especially big pleasure because I grew up here in Chennai. Essentially, within a mile or two of this point is where I spent all of my childhood, my schooling, even my college education was about 20 miles away in Tambaram. So, you know, Chennai has got a very special connection for me. So I want to give a talk. This is in astrophysics. So in fact, this is an astrophysics session on black holes, on things related to some extent to what Priya said. But on the other hand, I'm going to make this a talk for physicists. Okay, this is really addressed to a physics audience. I think this is too close. I think that should be enough. You can hear me, right? Yeah, that's better. Yeah, so this, I'm going to try and focus on physics, but the objects we'll talk about are very much astrophysical. A lot of the preliminary background stuff has already been described in a number of talks. Abhay gave a nice introduction to just what black holes are. Priya told us about accretion, and other speakers have spoken. So I can go through some of these things rather rapidly. So I'll remind you what we mean by a black hole. It's an object that's very different from everything else we know. This is what I would call a normal object, which is not a black hole. You know, it's got some stuff, some matter. It's got a finite density. It's got some radius. There is some surface, and you can say there is something inside. There's nothing outside. The Earth is a normal object. The sun is a normal object. A white dwarf is a normal object. A black hole is different. This is an object in which the gravity is so strong that nothing stops it from just collapsing down, and everything goes down to this point, the singularity that Joshi talked about a lot yesterday. And surrounding the singularity is an event horizon. And in fact, the black hole is defined by this event horizon, which behaves like a surface in the sense there is an inside and an outside, but the beauty of this event horizon is that it's a one-way membrane. You can throw stuff in, light can fall in, you can fall in, but nothing that falls in can ever get out. Right? So this is one way, and this is what makes it so remarkable. Abhay actually gave a nice example how in Newtonian physics this would be very hard. If you had such a surface, and if you just put a mirror here, if you shine a ray of light and it reflects off the mirror, it's going to come back, right? How can it not get out? This is just not allowed in Newtonian physics, but general relativity does things for you. This is quite a remarkable concept, the idea of an event horizon. This is a concept that comes out of general relativity, and you have solutions, the Kerr solution, the Schwarzschild solution, etc. And you know, but many people have wondered whether these things are real. You know, just because the equations give you a solution doesn't mean that you have to believe that this is how really nature works. And you know, you always suspect that perhaps nature is more clever than we think. It's got some way of avoiding the singularity, which is, of course, a terrible thing. You know, maybe long before quantum mechanics comes in and quantum gravity comes in, maybe some other physics will avoid the singularity, and maybe the event horizon itself can be avoided by some physics that we are not familiar with. And as we heard from Professor Narlikar's talk, there is a hint that at least earlier in his career, even Chandrasekhar, perhaps influenced by his debate with Eddington, I don't know, was a little suspicious of thinking about, you know, collapse down to a regime where general relativity might operate. And I think many other scientists have worried about this. However, we know from observations that there are black holes in the universe, and not just a few, huge numbers of black holes. These black holes that I'm going to talk about now, these are objects compact objects, and they are compact objects which are so massive that we don't think they can be anything else. We have a nice theoretical understanding of compact stars, beginning with Chandrasekhar's work on white dwarfs, followed up by neutron stars and other kinds of stars. And everything tells us that you can only have compact stars up to about a maximum of 3 solar masses. So if you try to make a compact star, that is a dead star, with a mass greater than 3 solar masses, it has no option other than to become a black hole. This is what theory tells us. Observations also tell us, if you go and look at all the neutron stars that people have discovered, nothing has been found more massive than about 2 solar masses. Seems to be consistent with the theoretical prediction. So in fact, what we do in astrophysics is you go and look for compact objects, and when you find a compact object that is more massive than 3 solar masses, you say, look, it has to be a black hole, and you label it a black hole. And by this criterion, we got many, many, many black holes in the universe. So there is one class of black holes. These are the more numerous class. These are stellar mass black holes, masses typically in the range between 5 and 20 times the mass of the sun. And our estimate is that there's probably 10 to the 7 or more such black holes in each galaxy. Like our galaxy has at least 10 to the 7 of these. And some handful of these are actually detected. These are special black holes that happen to be in binary systems. These are called X-ray binaries. So this is my compact star right here in the middle. It's this very compact relativistic object. It's got a normal stellar companion. Gas is flowing. It's actually being tidally ripped out of the companion, dragged in. Because of angular momentum, it goes into orbit, and then it slowly comes down to the center. And while the gas is coming down, and I'll say a little bit more about this in a couple of minutes, it becomes hot and it shines, and you see X-rays, and that's how we discover these objects. Without this companion star, this black hole would be very difficult to observe, because it will just be sitting by itself doing nothing. But because of the companion star and the presence of gas, it becomes very bright, and we see them as X-ray binaries. And we know about 20 to 40, depending on how you count, of such objects, which are all black holes, because they all have masses in this range. There is the second class, which is what Priya focused on. These are the supermassive black holes. This mass range 10 to the 6 to 10 to the 10 solar masses. And this basically looks like there's one in the center of every galaxy, at least in the nearby universe, almost without exception. There are 1 or 2 exceptions, of course, but almost without exception, every galaxy, including our own, has got one of these big ones in the middle. Okay. So the question that I'm going to address is, are these really black holes? These are the things we know for sure. They are compact. In many of these cases, you can show quite plausibly that they are within a few Schwarzschild radii. The Schwarzschild radius, as you know, is the radius of the horizon of a black hole, of a non-spinning black hole. So you can make an estimate of the size. The size is, just about right. The mass is right in the sense theory says if you're over this mass, it has to be a black hole. And these are all objects that are above this, and in cases of these supermassive black holes, way above this limit. But that's still not really proving that they are black holes. It's just proving that they are objects that we don't know how to model. What I would like to ask is, can we find independent evidence? Some of the colors are not coming for some reason. Can we find independent evidence that our black holes actually have event horizons? Because remember, the definition of a black hole is an object that has an event horizon with a singularity inside, but the event horizon is the key. Black hole, if you go look in the textbook, physics textbook, it won't tell you that a black hole is defined by mass greater than 3 solar masses. That's something that comes from a model. This is the defining property. And so, this is a question that I think is fairly interesting. Do these objects that we have been calling black holes, do they have event horizons? Now, how are we going to check or find evidence for the event horizon? It's very hard. Of course, you have to go right down to the center and look at what's going on there. These accreting systems, systems in which gas is flowing down to the center, are the only chance we have. I won't say only chance, but the best chance we have. The reason is that the gas is shining, so it's sending us some information. We can see the data, observations, And the gas is also going right down to the center. So it's looking at what's going on right down there. And it's only a question of us being smart enough to interpret the data, that the radiation that comes from the center, and see whether it can tell us something about the nature of the central object. So this is what I'm going to talk about. How to use this accretion disk and the radiation it produces to say something about the nature of the central object, perhaps to find evidence that there is this one-way membrane, the event horizon. This is a question that actually we asked, I think, as far as I can tell, for the first time, about 15 years ago. So this is that first paper that we wrote, where we first posed the question, can we look for evidence for the event horizon? And then we presented the first kind of tentative evidence in favor of some of these objects being really black holes with event horizons. And then, that particular first argument has become much stronger over the years. I won't say anything about this because it's a little bit too astrophysical, and I think this audience will have difficulty keeping track of all the phenomenology. Many other arguments have been made, mostly from our group, but also from some other groups. All of these different arguments, even though I won't describe them to you, I can tell you in brief, they all come back with the same answer. These objects that we have been calling black holes are really black holes. In the following sense, they don't have surfaces. That first picture I showed, what I consider a non-black hole is an object with a surface where stuff can fall and stick, etc., and signals can come out. All of these arguments indicate that our black holes really are black holes. Today I'm going to talk about just one of these arguments, which I think is a nice argument, perfectly suited for a physics audience and for students, because the physics I'll use will be really basic physics. I think a good undergraduate can follow, and certainly any graduate student should be able to follow at least the logic and the physical principles. So I'm going to just focus on this particular argument. So let's go a little bit into the physics of accretion, which Priya has already explained. So you start with some black hole in the middle. You start with some gas going around it. It's slowly spiraling in. And as it's spiraling in, of course, it's falling into the potential well of the black hole. So the gas is losing potential energy as it falls in. It's gaining some of it back in the form of kinetic energy, because the thing is in orbit, and as it goes to the center, it's going to go faster and faster, Kepler's laws. But it doesn't get back all of the energy. Only about half of the energy that it loses in potential energy comes back as kinetic energy. The rest comes out as heat. It's just simple energy conservation. If you take gas from here and put it here in this orbit, there is some leftover energy, and that was all dissipated along the way into heat through viscosity or something. You don't need to know what it is. Some amount of energy goes into heat, and when the gas gets hot, it will radiate, and so ultimately it comes out as radiation. So this is the basic idea of accretion disks, that potential energy is converted into orbital kinetic energy and thermal energy. The thermal energy is radiated, and this is the key point. This radiation will come partly from the accretion disk and partly from the surface of the central object, if there is a surface. If it is a black hole, there won't be this component. You'll only see the disk component. So here is my schematic picture. There is an accretion disk. It's producing heat and radiation. There is some fraction of the luminosity of the system which comes out from the accretion disk. I'll call that L sub accretion. Some fraction comes from the surface of the central star. I'll call that L subsurface. And what I'm going to now show in the next few minutes is that, in fact, the surface luminosity will usually be of order, the accretion luminosity, or even larger. That is, this component of the luminosity is not a negligible small perturbation, but in fact, it can often be the dominant component in the luminosity that comes from the system. Unless, of course, there is no surface. So this is where the key is, right? If there is a surface, there will be a component which will probably dominate the emission from the system. But if it is a black hole, this component will be missing. And so this is where the argument is going to go. And I'll repeat again that really this argument is kind of very robust, because it's really just using energy conservation. Not a lot of detailed gas dynamics and other stuff going in. You're just looking at GM over R. In fact, let me go to the next slide to give you an idea of how these numbers work out. So let's imagine that you've got Newtonian physics. So you've got an accretion disk with gas going around essentially in circular orbits. When it's at a very large distance, the gas has essentially zero binding energy. Its potential energy is almost zero, its kinetic energy is almost zero, total energy is almost zero. When it comes down to the center, so let's say it comes down to the center to a radius r star, the total potential energy it has lost is gm over r. But at that radius, if you calculate what is the kinetic energy of the orbit, circular orbit, it is gm over 2r. So half of this energy is still sitting in the kinetic energy, half is remaining in has been converted to thermal energy. So the half that has been converted to thermal energy between infinity and r star, that is all going to come from the disk. So from there to there, half of gm over r star has been released as heat. All of that will come as accretion luminosity. But then what you've got is this piece of gas which is now zipping round and round very fast with a kinetic energy of gm over 2r star. Then it's going to fall on this central object and stick to the central object and essentially come to rest. I'm taking a simple picture where this object is not rotating, okay? So it's going to suddenly go from all that kinetic energy to nothing, no kinetic energy. So all of that gm over 2r star will come now from the surface. And it's essentially the same as the amount of luminosity coming from the disk. So that's where my statement comes that these two are of the same order. Here the symbol m dot is again something that Priya introduced. So when we think of accretion, we imagine that you've got a steady flow of gas. Gas is flowing in at a rate m dot, so many grams per second. And so the luminosity is given by the grams per second multiplied by the energy released per gram. Okay, so you can see where the units come from. Okay, now we can, of course, to this audience, I cannot just give Newtonian analysis and say I'm done. Obviously, I have to do the things in relativity. And this is one of those problems where, at least for the Schwarzschild case, it's really a nice exercise. Every student should try these things because you can calculate everything from first principles. There are nice equations and all that. So you have to look at the energy per unit mass at infinity, which is 1 in our geometrized units. You can look at the energy per unit mass of a circular orbit at some radius, of a material at rest. And then you can do all of these calculations, how much energy goes into the disk, how much goes into the surface, et cetera, et cetera. I've just got some numbers here just to give you a flavor. If I have a star, non-spinning star, and if its radius is equal to 6m, which for those who know is the radius of the innermost stable circular orbit, the ISCO, so-called. That's a very characteristic number. For this case, if you do the relativistic calculation, you find that the disk will produce a luminosity of 0.06 m dot c squared. The surface will produce a luminosity of 0.13 m dot c squared. So the surface will be about twice or 2.5 times greater than the accretion disk. If I go to another very interesting limit that I won't have time to talk about, so-called Buchdahl limit, which is in some sense the smallest radius of any reasonable stellar model, which is 9/4m, the disk luminosity will be this much, the surface luminosity is about 10 times more. And if you then take liberties with your physics and go into some very strange models called Grava stars and others, where you make the surface almost the same as the horizon. So what you have in your mind is a picture where it's not a black hole, but its size is practically a black hole. So just outside the horizon, you put a surface, and you arrange things so that it won't collapse. So that's a Grava star. Then it becomes about 15 times larger. So this is just to confirm that the surface luminosity is always large. So now let me go to my evidence. I'm going to kind of present this as a kind of a logical argument. It's going to use some simple physics. Some of it is actually quite pretty. So I hope you'll appreciate how basic physics ideas can be used in quite powerful ways when you're faced with new questions. So I'm going to do two parts in my talk. First, I'm going to give you the evidence, which itself has got a number of logical steps. And then I'm going to discuss, depending on how much time we have, loopholes. How do we break this evidence? How do we break the logic? Is there some way to get around these arguments? And then we'll conclude. So the object I'm going to talk about is the big black hole at the center of our galaxy. We have seen this in several talks already. there is this dark object in the center of our galaxy. It seems to have a mass of around 4 or 4.3 solar masses, 10 to the 6 solar masses. And you have heard about the evidence. The evidence is we see stars going round and round in the center of our galaxy in Keplerian elliptical orbits. And from the orbits, you can calculate where this, the central attracting potential is, where is the mass, and how much mass is there. So we know that the mass is exactly here at this plus point in this movie, and the mass is, several million solar masses. Beautiful observations, but I won't dwell on it because you've already seen this. So we'll start with this. There is something very massive and pretty compact. Not very, very compact, but these observations by themselves can't tell you how compact it is, but it is compact, say less than about 1,000 Schwarzschild radii or some such thing. Next fact I want to introduce is that there is a radio source, an object producing radio waves called Sagittarius A star, which is located exactly at the position of this plus. Okay? Exactly there, to within the measurement precision that we have, there is a source of radio waves. And of course, everybody has assumed that it is this dark object, that Sagittarius A star and the dark object are the same object. And for most people, that's good enough, because the chance of some random, extraneous object being exactly in the same location is extremely small. But there is one extra nice, beautiful piece of evidence that Sagittarius A star is exactly the same as the dark mass, which is the following. Using, wonderful radio interferometric methods, Reed and Brunthaler, actually Mark Reed has been doing this for many, many years, have looked at this Sagittarius A star and looked at its motion in the sky. So what you do is you look at it over a period of 10 years, say. You look at it and you look also at some very distant background object, one of the quasars that Priya talked about. We know that the quasar is so far away it doesn't move, right? It's a fixed object. You look at how Sagittarius A star moves relative to this background frame defined by the quasars. And what he found was it is moving. It's moving with a nice linear velocity in the plane of the galaxy. So we have, our galaxy, is a plane. So in the plane of the galaxy, it's moving with some velocity. And it's got a tiny velocity perpendicular to the plane of the galaxy. Okay. Then you tell yourself, wait a minute. I'm not sitting on a stationary platform. I'm attached to the Earth, which is attached to the Sun. And the Sun is going around the galaxy, right? So here is Sagittarius A star at the center of the galaxy. We are sitting on the Sun, and the Sun is going around the galaxy. So you have to remove the motion of the Sun and then ask what's left over, because that's the real motion of Sagittarius A star. And then what you find is this motion here in longitude as well as the motion in latitude is entirely due to the motion of the Sun. So you go and you subtract out whatever motion, we know the motion of the Sun. So you subtract it all out, and then what you're left with is 0. Sagittarius A star, this is remarkable for an object at the center of our galaxy. To measure velocities at this precision, it's just mind-boggling. But this is their estimate of the velocity of, that is the linear velocity of Sagittarius A star, minus 0.4 plus minus 0.9 kilometers per second. It's at rest. It's just sitting there doing nothing right in the middle of our galaxy. So what? Well, the point is, this guy is sitting in the middle of all these stars, right? There are stars running around. They're running around at hundreds of kilometers per second, or thousands, or even some of them are 10,000 kilometers per second. This is the system. You should think of this as a statistical mechanics system. There's this massive object here in the middle, Sagittarius A star. There are other stars going around. They're all interacting through gravitational interactions. It's like a gas, except that it's interacting through gravity. Ultimately, it has to come to thermodynamic equilibrium of some sort. And what you would expect is that the temperature of this object, as described by its random velocities, should be of the order of the temperature of the rest of the stars. This is the theory behind Brownian motion, as you all know, right? Brownian motion, you can put a big particle, but it'll still be moving around because it's being bombarded by all the atoms and molecules in the gas surrounding it. So you can do now Brownian motion analysis on Sagittarius A star and say, how can I get such a small velocity when everybody else is running around at hundreds of kilometers per second? The way to do it is to make this object much more massive than everybody else. The more massive you are, of course, the more slowly you move at the same temperature. KT is half mv squared, right? So you can do this calculation, and this is what they did. This guy, Sagittarius A star, as an object, has to be at least 10 to the 5 solar masses. It's probably 4 times 10 to the 6 solar masses, but the thing is, it's at least 10 to the 5 solar mass. It's a very massive object. So this is, I would say, a beautiful confirmation that not only is it in the right place, it's also incredibly massive. And we already know that there is one massive object there, so they are the same object. Very good. Next step. I don't know how many steps I'm going to have time for. You'll give me warning, right? Okay, next step. Sagittarius A star produces radiation. We're going to use the radiation, obviously. You can go and look at the spectrum of this radiation. So here is a plot. Don't worry about the axes. This is a measure of luminosity, ergs per second, coming out of this object as a function of the frequency of the radiation, going all the way from radio to X-rays. This guy produces most of its radiation in the band around the sub-millimeter. And the luminosity is about 10 to the 36 ergs per second. So this is where the bulk of the emission is coming from this object. As an aside, 10 to the 36 is an incredibly low luminosity. If our central black hole were doing the kinds of bright quasar-like things that Priya talked about, it would be 10 to the 44 ergs per second. So this was her statement, that our galaxy and many nearby galaxies are very, very different from what we see in the distant universe. These are very, very underluminous. This is not relevant for my talk, okay, but just as an aside, a point of interest for students. So 10 to the 36 ergs per second is coming out here. Now we want to know, okay, I've got some radiation coming. Which component of this radiation, of the radiation in the model is this? Is it coming from the disk or is it coming from the surface of the star? So I'm going to prove, I think, beyond any doubt, that this is coming entirely from the accretion disk. So where is the proof? The proof comes from the following, that people have not just looked at the motion of Sagittarius A star, they've also measured the size. You know, with a good radio telescope, you can make an image, a picture on the sky, and find out what is its size. And it turns out that Sagittarius A star, the part that is producing radio emission, is just a few Schwarzschild radii. So it's as small as what you would expect a black hole to be. It's very, very compact. Then you can do a very simple calculation that astronomers do all the time, radio astronomers in particular. Once you know the flux that you're receiving from an object and the size, you can calculate something called brightness temperature. So let me tell you what brightness temperature is. Brightness temperature is the following. It is the temperature that an object must have in order to produce the observed flux at a given wavelength. So brightness temperature can be a function of wavelength, but at a given wavelength, so in our case we are going to look at sub-millimeter. So the brightness temperature here will be defined by saying, given the size of this object, what temperature should it have to produce via black body radiation this much flux? So it's something that is rooted in black body theory. So you just say, if it is a black body, it must have had such and such temperature to produce this flux. In this case, it is 10 to the 10. So the brightness temperature is 10 to the 10 or a bit more for this object. The beauty of the brightness temperature is the following, that if an object has a brightness temperature of TB, then you know that the gas that's producing the radiation has to be at least that hot. Because nothing can radiate more than a black body, except things like lasers and coherent sources, which we are not dealing with. Incoherent sources cannot radiate more than a black body. So if you know the brightness temperature, it puts a limit, a lower limit on the temperature of the gas. You can be hotter. It's possible to be 10 to the 12 degrees Kelvin and have a brightness temperature of 10 to the 10. The way you do it is by making the object transparent. It's not radiating all of the energy it could. It's because it's transparent, you get less radiation. But you can't radiate more than black body. Think about it if you have not considered this point before, because it's a very powerful point. And this is why astronomers use it all the time. So we have this now conclusion that whatever is producing the radiation is at least 10 to the 10 Kelvin in temperature, perhaps a bit more. Then the next point I want to introduce, as I said, this is an exercise in logic, right? The next point I'm going to introduce is, if I have a surface, the surface will produce something closely resembling black body radiation. In fact, later on I'm going to argue that it will be exactly black body, but for now take it that it will be close to black body. The reason is, I've got objects that have been living for 10 to the 10 years. They must have reached some kind of steady state. There's some rate at which stuff is falling in, it's producing radiation. Steady state means that there is some temperature, some characteristic temperature associated with the gas, and it's going to be very, very opaque, right? We've got 4 times 10 to the 6 solar mass of stuff. So that's going to be tremendously opaque at all wavelengths. And we know from theory that if you have gas at a certain temperature and if it is completely opaque, it will radiate black body radiation. That's how we make black bodies. You fix the temperature, make the thing opaque, let it reach steady state, and out comes black body radiation. The only way to deviate from black body radiation is to make the object transparent. Again, I'm going back to the previous point. If it's completely opaque, it will be black body radiation. And our surface is going to satisfy these constraints. So I expect black body radiation from my object. So now let's start with this fact. Gas is at least 10 to the 10 Kelvin. If the gas was radiating from the surface, it will radiate black body radiation. And I know how to calculate black body radiation at 10 to the 10 Kelvin. So I can calculate it. And what you'll find is, you would predict that the peak of the emission would come in gamma rays, not in the submillimeter, obviously, right? Something at 10 to the 10K is going to radiate in gamma rays, most of its energy. And it will have a luminosity of 10 to the 62 ergs per second, which is more than, any reasonable luminosity anybody considers for anything. Basically, what I'm saying is, the emission here at this wave band requires a brightness temperature of 10 to the 10 Kelvin. If the object were truly a black body at 10 to the 10 Kelvin, it will of course fit this data point, but it will keep going up, way off the roof of this building, up to 10 to the 62, out there at a frequency of 10 to the 20 hertz, and then fall down. That's where all the energy would be coming out if it were an opaque black body source of radiation. In fact, this is not that. This guy is just doing this much, which means it is really transparent. It is transparent over all of these wavelengths. It may or may not be transparent here. We just don't know. But it's at least 10 to the 10 Kelvin. Okay? I consider this a pretty solid argument. But again, if many of you have not seen such arguments before, it may take a little getting used to. So I can say for sure that Sagittarius A star is not putting out 10 to the 62 ergs per second, nor is it producing that kind of luminosity at X-rays and gamma rays. Therefore, the radiation must be emitted by optically thin gas, which is the same as saying semi-transparent or transparent gas, at least in these bands, the infrared, X-rays, and gamma rays. Therefore, given that a surface will emit black body radiation, this radiation is not from the surface. Okay? So that's the argument. It must be from optically thin gas in the accretion disk. Fine. So now the question is there surface luminosity? There should be a second component. If there's a surface, there should be a second component. And that second component must have a luminosity at least of order the accretion luminosity. At least about 10 to the 36 ergs per second must be coming out somewhere else in the spectrum. And you can go and look for it. Now here is where, again, black body really comes to our rescue. You can't put it anywhere in the spectrum you like, right? You can't just say, I don't have data here. Why don't I put it there? The point is, black body is completely constrained. Planck has told us what it will do. And if you know how much luminosity you expect, you know exactly where the radiation will come, what its spectrum will look like, etc., etc. And the beautiful thing is, in the case of Sagittarius A star, if you simply postulate that it has a surface and calculate where this extra radiation would come, it would come out in the infrared. And in the infrared, we do have observations. We have upper limits on the flux of Sagittarius A star, steady flux in the infrared, and there is no sign of it. This is the plot I'm going to show. So 4 wavelengths where there are some upper limits on the flux of Sagittarius A star, 1.6 microns, 2.1, 3.8, 4.8. So the real flux is less than this. You can choose any radius you want for this surface. So I've used 4 radii here. I made it exactly equal to the horizon. I made it twice the horizon, 4 times, 8 times. And these are the predicted fluxes from this black body model for surface emission. And in some sense, these are the minimum fluxes you expect. It could be a lot more. It cannot be less than this. And there is a discrepancy at every wavelength. And please note, this is a logarithmic scale. You may think, it's not very far. I can do it. But we are talking about tens, factors of several tens discrepancy. And probably it could be made even stronger with more work. But it's already done in some sense. I don't think there's any need to do even better than this. So that's the argument. Okay? This radiation is missing. It cannot have a surface. Therefore, it must be a black hole. Here is the summary of this, the logic here. There is a dark object. There is Sagittarius A star. And I think I convinced you that they are the same object. Several times, a million solar masses. The observed radiation from this object, Sagittarius A star, is from the accretion disk, not from the surface, because its brightness temperature is too high. Then we say, if it had a surface, there would be a second component, which would be black body-like, which would have a luminosity of at least this much, and we can predict what it will look like. And we predict that it should come out in the infrared. We don't see the infrared. Therefore, there cannot be a surface. There is only emission from the accretion disk, i.e., there is an event horizon. Okay. As I said, there's only one of several arguments we have, but this is such a clean argument, I thought I would present it for a physics audience. Now, of course, immediately people say, okay, it all looks very plausible, but there is all this chain in the logic, something may be going wrong. Plus, I'm not sure you all the relativity properly into your calculations. So I'm going to deal mostly with the relativity for the rest of the talk, for which I have some more time. Yep. So the way relativity comes in is through enormous redshifts and time delays and things like that. Right? You all know the fact that as you fall deeper and deeper into the potential well, there is a larger and larger gravitational redshift. Things get redshifted as they come out. Things also come out slower. In some sense, it takes longer for signals to get out. All of these are effects that are not captured in any Newtonian thinking. And so, there is a suspicion that if we did relativity carefully, it'll get around all of these arguments. In particular, you could imagine these gravastar models, which are, very, very strange models. I would say they're even stranger than black holes, but, we'll take them seriously, that have radii which are just marginally outside the horizon. So this is the horizon at 2m. I put a little extra delta r and make a surface out there. And if I make delta r small enough, I can get very, very large redshifts. And then with those large redshifts, perhaps I can completely kill the argument. The bottom line, in case I don't go through everything, no. We have looked at many ways that you can use redshift and relativity. Nothing helps. The logic, as I presented, just goes through fine. But let's go through some of the questions that one could ask. I've got kind of 4 points here, and hopefully we can go through all of them. This is the first and probably the easiest to dispose of, where we are all taught when we first learn relativity that signals take forever to come out from the horizon, right? In fact, there is this whole argument about if somebody falls in, you never see them going through the horizon because everything gets slower and slower and slower, and it takes infinite time for signals to come out. This is a statement, but it's an infinity that's only a logarithmic infinity. Okay, this is the part that people sometimes miss. If you ask how much extra time compared to this simple Newtonian straight line motion, how much extra time does this photon take to come out? These are numbers for the galactic center black hole. 40 seconds times logarithm of this quantity. This is my delta r, so you remember? That's the little bit by which I have moved the surface away from the horizon. Think of this as radius of the horizon. So radius of the horizon over delta r, logarithm. Now this is, we are talking about objects that are 10 to the 10 years old. And we're talking about 40 seconds. And you want the logarithm to be large enough to have, prevented the signals from coming out. What this means is this business about signals taking forever to come out. The argument is the following. The thing surface is there, it is radiating, but the poor radiation hasn't yet come out. It's still fighting to get out of this potential well. Well, it's only fighting a logarithm. So, your logarithm has to be enormous. And so, in fact, what you need is delta r over r star is, this is the kind of number, I think Abhay had an exponential of 10 to the 76. These are numbers you cannot comprehend. This is just unbelievable. I think this is crazy. We don't even worry about it. This is the argument that most people immediately worry about, which is just that redshifts all photons, right? So you can emit radiation from the surface, but if it's highly redshifted, by the time it comes to infinity, it has got so little energy, and also the frequency, the spacing between photons is so low, you're not going to see anything. This is in fact a false argument. And the reason is, I'll just give it at a physical level. All we're using is energy conservation. Physics will take care of the details. What did I do? I dropped mass on this object. Some amount of energy came out in the disk, and there's some more that should come out from the surface. And it has to come out, and it's reached steady state. How can it not come out, right? How can gravity come in and suddenly say energy is not conserved? So, I can go through details for people who want to look at it. You can look at what happens to individual particles, what is the energy doing, et cetera, et cetera. But let me just tell you very briefly how it works. Let us say that Sagittarius A star, we calculate it has a black body temperature of, let's call it 2000 degrees Kelvin. Okay? That is to say, according to our calculations, 10 to the 36 ergs per second luminosity would correspond, if you were to look at it with our telescope, to a temperature of 2000 degrees Kelvin. What the correct calculation will show you is, if you go to the surface of the star, the local temperature will be much more than 2000 degrees Kelvin. It will be greater by the redshift. So if I've got an enormous redshift of 10 to the 6 on the surface, the local temperature in this, when you do the calculation correctly, the local temperature will be 10 to the 6 times 2000 degrees Kelvin, and it will radiate locally at that temperature, such that by the time it reaches infinity, it will be 2000 degrees Kelvin. This is how energy conservation will be taken care of. Everything will work out fine. So I'll just make that as a statement. We can discuss if somebody doubts it, but this is actually a very obvious point. Actually, I've found that when I talk about this to physicists, it's much easier to convince them than the astronomers. Astronomers, the redshift. But yeah, so yeah, okay. This is the one I don't want to miss, because this is so cute. I really like this. The question is black body, right? Is my surface going to produce black body radiation? Now here is a picture. I don't think Abhay showed this, even though I think he had some of these concepts. When you are near a black hole, let's say I've got some observer here, located at rest. If this observer shoots out rays in all directions, you know that certain directions will just fall into the black hole and disappear. Those are all the rays inside this black cone. So there's one set of directions for which the geodesics are such that they just fall in through the horizon and disappear. All other rays will escape the horizon and reach infinity somewhere. Deflections and all that, but they reach infinity. So if I'm far away, of course, the little cone that falls into the black hole is very small. And as closer and closer, the cone gets larger and larger. If I come to a radius of 3m, this is the famous photon orbit, the cone becomes a hemisphere. So half the rays will fall into the black hole, half will escape to infinity. So a ray that I shoot almost tangentially here will kind of go round and round and then fall into them. But if I shoot it a little bit out here, it'll do that and then go off to infinity. Okay. Now I'm talking about very compact objects, right? My surface is inside 3m. In fact, it's at 2 plus epsilon m. So what happens as I come closer and closer to the center? What happens is that this cone almost covers the whole sphere. So out here, every direction I send out a ray, it kind of falls back on the horizon and falls into the black hole. And there's just one little hole right in the radial direction through which, if I shoot a ray, it can escape to infinity. Okay, so the closer I come to the horizon, the smaller the escape angle through which radiation can get out. So I'm talking about rays that I shoot, but this works also for every other point on the surface. So if the other surface is shooting out rays, it will reach me. So for instance, if this point out here shoots a ray out like this, it will probably reach me along one of these directions, and so on. So here is now the mental picture I want you to imagine. So here I am, imagine you're sitting on the surface, right? The surface looks like a nice sphere in these coordinates. But what will you actually see? You sit on the surface, any direction you shoot, except this one little small hole on the top, goes and hits some other part of your surface. Equivalently, you can see that part of the surface through a returning ray. So in every direction, you see other parts of your system. So you look up, and it looks as if you're sitting inside, not outside, inside a spherical system. Inside a spherical system, there's rays reaching you from every single point, except for this little hole in the top. And you reach steady state. You get cooking in this beautiful interior of a spherical box for 10 to the 10 years, okay? With a steady supply of heat and a steady leakage of energy, reach steady state. Now, I claim that this is exactly what a furnace is supposed to do. How do we make black bodies? At least this is what I learned when I was doing my BSc physics. Black body, the way to make it is make a nice, doesn't have to be spherical, but the book showed a spherical furnace. You put some heat, wait for it to reach thermodynamic equilibrium. Then you take a little pin or something and make a little hole, and through that hole will come out black body radiation, because this has completely, reached thermodynamic equilibrium. It's talking to itself all the time, and our black hole is going to do not the black hole, the non-black hole. The guy with the surface is going to do exactly that, because this is the geometry. This is the real geometry of geodesics, even though in our coordinates it looks quite different. So I believe that our surfaces are going to be not just good black bodies, but they're going to be absolutely the best black bodies you can imagine, because this angle becomes really small. The solid angle of this escaping hole goes like 1 over 1 plus z squared. So if you want to make a redshift really large, it's going to be smaller than any laboratory pinhole you can think of, and you'll get your perfect black body. So I think the black body is a good assumption, at least for these relativistic objects. This is not Hawking radiation at all. Oh, this is classical thermodynamics. I'm actually adding mechanical energy, converting it to thermal energy, and letting the system come into equilibrium. And then I'm bleeding out some radiation, which reaches me at infinity at 2000 degrees Kelvin. Yeah. Local temperature is higher, as we talked about. So last thing somebody can ask is, how do you know the radiation is what it will emit? With those enormous temperatures, enormous redshifts, maybe there are funny particles, and maybe what will come out is particles. Again, I say physics tells us the answer. Once you have said thermodynamic equilibrium is such a powerful, powerful statement, all answers are immediately given. Thermodynamics tells us that if something comes out with a temperature T infinity, and it's the black body or thermodynamic equilibrium system, it will consist only of radiation and particles with mc squared less than kT. Any other particle that might have been produced in that furnace or in the, on the surface where the temperature can be very high will not escape, because it won't be permitted by thermodynamics. So you may get some neutrinos out of the system if you can make neutrinos. But neutrinos, as you know, can only introduce a factor of 2 correction to what the photon emission is at best. So that doesn't change anything. So, I've looked at the physics part of it, the relativistic physics part of it, and maybe we are not just clever enough. There are some other things yet to be considered. But so far it looks like these very simple energy arguments will survive. They're not going to get swamped by anything sudden and qualitative. But there is, of course, astrophysics. There are some astrophysical assumptions, and the one key assumption we have made, or I have made in this talk, is to say that the emission that we actually see is from accretion. So, that was one underlying paradigm, that there is actually accretion going on, and then it produces 2 kinds of radiation and all that good stuff. But suppose this object is not accreting at all, it's producing radio emission through some other mechanism, then of course we are completely dead. Then the entire argument falls down. But then, I can give various astrophysical arguments why this is extremely unlikely. In fact, Priya has already introduced that by saying our galactic center is already extremely dim. We are fighting to understand why it is so dim, because it should be a lot brighter. Now, if you're going to say that even what little we see is not accretion but something else, then the problem just gets so much worse. So, but this is just to make a complete story. There are ways to get around, but they would be astrophysical rather than physics. One final point. No surface, does it mean event horizon? Right? I'm not saying, I've not proved that there's an event horizon. At best, I have proved that this object does not have a surface the way we understand surfaces. There are models you can come up with which are neither surfaces nor event horizons. Yeah, I'm done practically, yeah. 10 minutes, thank you. Okay, we can have discussion. So, there are other options, but they are more bizarre. I don't even want to deal with them. Oh, yeah, maybe since I've got 10 minutes. Damhour and Solodukin said, oh, no, they can be wormholes. So, you can have a wormhole model, and they had a wormhole model in which they had some parameter. And, that their wormhole actually will return radiation. But they said, I can hide the radiation if I make it such that it takes forever to come back. It's exactly the same as the argument I had earlier. What do I need? How compact should I make an object to prevent the radiation from coming out through sheer time, just taking forever to come out? It's the same argument. In fact, the answer is the same. What they say is they need a wormhole with some parameter lambda less than e to the minus 10 to the 15. So if you can do that, in fact, you can do a gravastar with that same parameter value, then of course you can completely avoid all of these arguments. It's some parameter. It's some ratio of one length to something else. It's like in my previous case it was delta r over r horizon. This is some other length. Actually, I don't even know what it is, but it's of the same flavor. So, if you can do that, fine. But, is a wormhole so much better than a black hole? I don't know. This is the one that really interests me, the naked singularities. The whole business of the horizon is it hides the singularity. But, I think Pankaj Joshi gave us, reasons to think that naked singularities are possible. And the question is, can you have long-lived naked singularities? And could they masquerade as black holes? Because the naked singularity, again, doesn't have a surface, right? I don't know what it is, but at least it's not a surface. And what I would really like to know, and I hope Pankaj will help me to figure this out, is if I have accretion on a naked singularity, what will it look like? Will it behave like a horizon that just sucks up everything and no extra component of radiation? Or will it behave ultimately like an object with a surface, and therefore can I use arguments similar to what I described here? So I hope we will figure this out at some point during this meeting or later on. But this to me is an open question. My gut feeling is that a naked singularity, it's naked means it's visible, right? If it's visible, I think it must be producing some measurable radiation. Not intrinsic radiation. I'm not talking about Hawking radiation. That can be redshifted like we talked about yesterday. But now we are actually dumping stuff, and energy has to be conserved. So stuff has to come out. And that part of the argument seems to me should be robust. But I would love to make a real solid proof of this, to satisfy physicists. Okay, so that's the kind of the various escape hatches, loopholes. So here is a summary of what I've said today. We have now a number of arguments, maybe 4, 5, 6, quite distinct arguments, all of which are telling us that one or more of our black hole candidates cannot have a surface. Each of these arguments you can get around in some, complicated, convoluted way. There's always a way to get around any evidence you produce. But the way you solve the problem for one argument will not work for another one. You have to come up with yet another excuse and yet another excuse. And so, it's beginning to look like, these really are black holes. That at least they don't have surfaces. Leave out this if we can still discuss this. But they don't have surfaces. I think, there probably are black holes. Event horizons are real. GR got it right. And even though it's weird and mysterious and strange and all that, that's how nature works. And I find that absolutely amazing and thrilling. Thank you.
It's an outstanding lecture, no doubt. but there'll be some questions, I'm sure. TRG.
A naive question. For the Hawking radiation, is there a way in which you can do similar analysis?
The problem is Hawking radiation temperature is too low. So, even a 1 solar mass black hole is some 10 to the minus 7 Kelvin. These guys will be 10 to the minus 13 Kelvin.
Okay.
The universe is full of so much radiation and other stuff.
Okay.
The only way we'll see Hawking radiation is by looking at mini black holes.
I see.
And people have considered that. So far, nothing has been found. The ones I'm talking about, you can ignore Hawking radiation completely.
But is there a way for the solar mass black holes?
Yes.
Some analysis of this thing is possible?
For Hawking radiation?
No, for the seeing no surface.
Yeah, not this particular argument.
Supermassive.
In fact, our first argument was for the solar mass black holes.
Okay.
Yeah. That's where we started our argument. And just to give you a flavor there, that was a different logic there. But one nice thing about the X-ray binaries, nice thing is we have many X-ray binaries with black holes, but we also have many more X-ray binaries with neutron stars. We know they're neutron stars for various reasons. So then, you've got this control sample. You've got a control sample with accretion and an object that has a surface. And then you've got your test sample here. You think it doesn't have a surface, but you want to test it. So you have a way of comparing. I can't do that for the galactic center, but there I can do it. And so we have a different line of argument, which is also giving, really strong evidence, I think, that there again they have event horizons.
Okay, this is with relation to the naked singularities business. So just when the naked singularity has formed, as Professor Joshi showed yesterday, that some radiation might just go out and reach Sky Plus. But just after the naked singularities have formed, the event horizon just starts growing up and just hides that. So how can we distinguish between the two? I don't see any.
Absolutely. No, you're absolutely right. The naked singularities that Pankaj talked about in his talk mostly were the kind that you talked about, you're mentioning in your question. Namely, a naked singularity forms, but very soon it is covered with an event horizon. And after that, you don't see the naked singularity, except during that initial burst you would see it. Those are no good for me. They are, as far as I'm concerned, black holes, because for most of the time they look like black holes. But there are other naked singularity solutions which are long-lived. Whenever you look at them, there's still a naked singularity. So it doesn't disappear after an initial burst. And it is those objects that I would like to constrain. Is it possible that some of our black holes are really those kinds of naked singularities or not? The other kind, I don't know how to constrain. I cannot, because it's too transient. It comes and goes.
Well, it is along the same lines. The argument here shows there is no surface, not that there is an event horizon. In fact, event horizons cannot be detected except on Sky Plus. So why should these be black holes?
Absolutely, yeah. Tell me what else they are.
Unless you do something like what Abhay says, some modification of...
Sure. No, I completely concede this point, and I hope I said it in my talk. I cannot prove the event horizon. I can only tell you that it doesn't have a surface. And then you have to tell me what else it is. And the only things people have told me so far are, oh, they're wormholes, or they're naked singularities. If you have another object, I would put that there,
Because, so, I mean, one cannot prove a thing by saying, what else can it be? That is not a proof, no? Or some other signal, or some other criterion.
The question is, what is proof? And how much evidence do you need?
I was just curious. So you mentioned, dark energy stars. So would they really fit the bill, or it's just an option which is a sort of an object which is slightly greater than the event horizon? I mean, how sort of efficient that could be to serve your, the object that was under discussion?
See, the dark energy, I mean, it's a serious model. Okay, people have actually developed a model. And it all goes back to this so-called Buchdahl limit. Buchdahl limit says, if I try to make a compact object with just normal matter, just think of it as an object in which the density only decreases as I go further out. You know, the pressure is maximum in the middle, so I expect the density also to be maximum in the middle. So if I say that my object is either has a constant density or a declining density, then it turns out that there is a minimum radius you can have. And it is not the horizon. It is 9 by 4 m. If I try to make it smaller than that, the center will become a black hole. It just exceeds. So there is a limit. Now this is a very, it's not very relativistic. At this 9 by 4, the redshift 1 plus z is only 3. Okay? 3 is nothing in our business. So if you want to make really extreme relativistic effects, you need to somehow push the surface down to the horizon, and you can't do it with normal equations of state. So basically what these dark energy star models are, my understanding is, you start with some kind of dark energy, a lambda, except lambda is not as small as the real universe. You tune it to whatever you need. So you put this dark energy fluid inside, then you put a little shell of normal matter on top, just at the radius you want, and you can tune it so that you can get any radius you want. So yes, it is a given, assuming that you will accept that you can have dark energy equation of state, which is, it's a strange equation of state. Assuming you will accept that, it's a valid model. It satisfies the, Tolman, Oppenheimer, Volkoff equation, and you can solve everything. You can get whatever radius you want. So I think it's a viable test model for such arguments.
Sir, Gravastar.
Yes, that's the same.
And there are very less probability that there will be stars of that kind. But given the number of stars that we have observed in the universe, there should be like at least few evidences of these kinds of stars. Have they been observed astrophysically?
Well, nobody knows how to make a gravastar. Okay? If you take a normal star, a big star, say a 50 solar mass star, and just ask what happens as it evolves and finally has a supernova explosion or a collapse or whatever. But I think they're allowed, as per Pankaj's work. You won't form a gravastar from such collapse because, there's nothing in our physics which says suddenly dark energy fluid will show up, right? We are made of baryons. Stars are made of baryons. There's no dark energy fluid there. So these are really models, right? Suppose there is a lambda or a dark energy, what kind of an object would I have? That's what these guys have calculated, and they found some solutions. No example has been seen. There is no viable route to make them, and so, that's the situation we are in.
Sir, by star formation theory, we know that very massive stars are highly unstable. And the most massive star is Betelgeuse, around 200 solar masses. Then how can you account for a star like Sagittarius A for 10 to the power 6 million, 10 to the power 6 solar masses?
Yeah.
How is it accounted?
It went through all the things that Priya talked about. By her story, Sagittarius A star might have initially started, in the standard story, it probably started as a 100 solar mass black hole and then grew through accretion and other processes over the age of the galaxy. The new story she presented, maybe it started off already at 10 to the 5, because she knows how to make 10 to the 5 in one go, and then probably then accreted and grew up to 4 times 10 to the 6. But in almost any scenario, Sagittarius A star black hole was not born with this mass. It was born with less mass, but over the age of the galaxy, it has accreted gas and grown to its current mass.